Welcome to the World Trade Center Health Program's March Research Webinar. We're very excited to have you here today, and there's a lot of great information to share. This presentation today is 20-year trajectories of PTSD and mortality in World Trade Center responders, and Dr. Mann will be giving the presentation today. And then just for awareness, our next webinar will be April 11th on aerodigestive disease in the World Trade Center exposed FDNY cohort, validation of biomarkers, and defining risk to tailor therapy by Dr. Anna Nolan. And you should have received that information invite earlier today. At this point, I'm going to turn it over to Dr. Brian Oliver, our medical officer of the World Trade Center Health Program, to introduce Dr. Mann.
It's my pleasure to introduce Dr. Frank Mann. He began his undergraduate studies at the State University of New York at Brockport, where he dual majored in psychology and philosophy. After work as a research assistant investigating the impacts of parental conflict on preschool children, he completed his PhD in only 4 years at the University of Texas at Austin, where he was a core member of the Texas Twin Project. He then did postdoctoral work at the University of Minnesota and taught research methods and statistics at Augsburg University. In the fall of 2020, he began working at Stony Brook University in the Department of Family, Population, and Preventative Medicine. Today, he will be presenting study findings from collaborative efforts at the Stony Brook University World Trade Center Health Clinic and with the FDNY. It's my pleasure to introduce Dr. Frank Mann.
Thank you. Thank you, everyone, for attending. Today, I'm going to be presenting 20-year trajectories of post-traumatic stress disorder and its relationship with mortality in the general World Trade Center responder cohort. So to start off, thanks to NIOSH and the CDC and the NIH and NIA for funding this research, and special thanks to Sean, Roman, and Ben for their continued mentorship and support. So I figure research questions are always a good place to start. So when tackling this 20 years worth of PTSD data, the first question I had in mind was, what's the yearly prevalence of clinically elevated symptoms of PTSD from, 2002 to 2022? How stable are symptoms over these 20 years of follow-up? What's the average direction, shape, and rate of change in symptoms? And are multiple groups or classes needed to adequately characterize symptom trajectories? What about individual trajectories? Specifically, what do atypical trajectories look like that deviate from average change? And how quickly do symptoms improve or worsen over this 20-year period? Does exposure severity and genetic liability for PTSD predict symptom trajectories? And then finally, do symptom trajectories predict mortality? So the measures that I used for this analysis is they're pretty straightforward and pretty limited in scope. This was, in some senses, a kind of pure longitudinal analysis. So the main criterion variable are PCL scores, the trauma-specific version for the DSM-4 adapted for the World Trade Center attacks. Most will be familiar with this instrument. It's a self-report questionnaire, and the responders are asked to rate how much they're bothered by symptoms in the past month on a Likert scale. And a sum score is calculated, producing scores that range from 17 to 18, higher scores reflecting more severe symptoms. And very often you'll see folks in literature use a 44 cutoff for clinically elevated symptoms. So in addition to this self-report measure, we also have a clinical diagnosis of PTSD, okay? And that was obtained by trained clinicians, of course, who are qualified to administer either the DIS or selected modules of the SCID. It was administered only once 10 to 15 years after the 9/11 attacks, on average 12 years after the attacks. Inter-rater agreement is high for a subset of independently rated audio taped interviews. And roughly a little over 7,000 responders completed either the skid or the disc. It's almost 60% of the total sample, which we'll get to in a moment. And we have over 1,000 lifetime World Trade Center related cases of PTSD. So that's approximately 14% of responders who completed the interview. And there were no significant differences in demographic characteristics, age, biological sex, race, level of education, between those responders who did and did not complete a diagnostic interview. And those who were administered a diagnostic interview had PCL scores at baseline that were negligibly higher than those who were not. Was technically statistically significant, actually quite a small p-value. That's due to the virtue of the very, very large sample size. But you can see here, I mean, we have less than a point for a mean difference on the PCL. And, you know, the Cohen's D with Hedges correction for an unequal sample size is very small, 0.03. So in addition to these two focal measures of PTSD, the PCL and the diagnostic interviews, I'm going to make a bunch of group comparisons based on clinical status throughout this presentation. So one contrast that is made is comparing the full sample of responders to those who have a lifetime diagnosis, which I'll refer to as cases. Another comparison that you'll see made is between cases, controls, which are those who were administered a diagnostic interview and didn't meet criteria. And then finally, those who weren't interviewed, which is another way of saying those who have missing data for the diagnostic interview. And then another contrast that I'll be making is between current and active cases, remitted cases, partial or sub-threshold cases, and controls in a subsample of 3,500 of the responders. These groups have previously been used in longitudinal studies of the World Trade Center responders. This study here that you see cited that was published in Psychological Medicine, led by Evelyn. These are the groups that I'm referring to. And in some ways, you can see here, this analysis followed up responders 12 to 14 years after 9/11 and estimated the, 11 to 13 years after 9/11 and estimated the trajectories across those years. And one of the analyses I'm going to be doing is the 20-year extension of that analysis using those same groups. So here's the data. It's very extensive, very impressive, spans from 2002 to 2022. This top panel here, this is the full sample. You can see that that column N for sample size, it increased considerably as the years progressed from 2002 to 2022. On the far right, you can see the internal consistency coefficients, Cronbach's alpha, omega tota, omega hierarchical, all evincing excellent psychometric properties of the PCL over this time period. And then the bottom half of the table is obviously structured the same way. And this is the subsample of folks who met diagnostic criteria and have a lifetime diagnosis of PTSD based on either the DISC or the SCID. And next, it's the same table, right, or same descriptive statistics and internal consistency coefficients, but now broken down in terms of visits or number of assessments that are obtained from each of the responders. So you can see the full sample is 12,822 responders. And then among those, 11,462 had one follow-up, 9,975 had two follow-ups, and so on, all the way down to 44 responders who had 17 follow-up assessments. And then the same repeated here for PTSD cases. There are a couple of PTSD studies in the published literature that span 30 or even 40 years. But if you look into the nitty-gritty details of those studies, they typically aren't measuring symptoms until many years after the exposure has occurred. And they also have a very limited number of follow-up assessments, typically 3 or 4 at most. So when you take that into consideration, keeping in mind that we have 20 years of data here of over 12,000 responders who provide approximately annual assessments of PTSD symptoms, there's an argument that in terms of providing detailed information for trajectory analyses, this is arguably the largest and longest study of PTSD to date. So moving right into findings, here we have the prevalence of elevated symptoms determined by PCL score equal to or greater than 44. It's scaled in terms of the number of cases of PTSD per 100 individuals at risk. And as you can see here, we have roughly an inverted U or arch-shaped trajectory of clinically relevant symptoms from 2002 to 2022, with symptoms peaking in 2011. And these rates are akin to those that other studies have published in combat exposed veterans. So thinking about like the prevalence of symptoms in veterans of the Yom Kippur War and the Vietnam War, which really speaks, of course, to the severity of the traumatic exposures that the World Trade Center responders endured. Now, here's that same graph, number of clinically elevated cases per 100 individuals at risk, but the y-axis has changed. So we have the full sample here plotted at the bottom, and the y-axis has been expanded upwardly to be able to capture the prevalence of clinically elevated symptoms for those who met a diagnosis of PTSD between 2010 and 2015. And as expected, the self-reported symptoms reach that level of clinical significance at much higher rates than what we see in the full sample, but the same general inverted U or arch-shaped trend is observable. Obviously, the dots or triangles are the point estimates, and the vertical bars are 95% confidence intervals. So here's again the same graph, but now the group contrasts are the full sample, the PTSD cases, the PTSD controls, and those who were not interviewed. As expected, the PTSD controls have the lowest annual rates of clinically elevated symptoms. PTSD cases stay up there. I just drew lines to connect them, so it's a little easier to follow. And those who were not interviewed have rates that are very similar to what we see in the full sample. Now, here are the 4 groups that were used in Evelyn's paper in Psych Methods. So now the bottom group are the PTSD controls. The green group is subthreshold or partial cases. The blue is remitted cases, and current PTSD is the highest group there. And they're rank ordered as one might expect based on, just basic intuition of what we think would happen with those groups. And at least for the remitted cases and the current PTSD cases, again, that inverted U or arch shape trajectory is evident. So next, moving on to our question about stability. So how stable are PTSD symptoms over this period of time? So I was primarily interested in addressing this question because I was wondering whether or not PTSD symptoms essentially met a set point theory of change over time. So with a set point theory, we would think that there's some underlying liability to manifest symptoms when you're exposed to a trauma. It's probably partially heritable. And what we would expect to see if the set point theory were the case is that we'd see initial drop in symptom stability over a 1 or 2 year time lag, but then start to see stability coefficients stabilize thereafter. As opposed to more gradual declines, more steady declines in stability over the 20-year period would really kind of be inconsistent with the set point theory and reflect more true change over this 20-year period of follow-up. So how do we estimate stability? Well, we calculate test-retest correlations, right? For each year of data collection, we can stratify them by the clinical status, those various groups. Obviously, higher retest correlations mean more stable, lower retest correlations mean less stable. And then you meta-analyze your test-retest correlations across different time lags, okay? And then you can plot your average correlations across increasing time lags for each group. Often these are referred to as longitudinal stability plots. I've also, in other fields, seen them described as variograms. So here's that longitudinal stability plot for the full sample in blue, PTSD cases in red, vertical bars denoting the meta-analytic confidence intervals. And what we do see here is that for the full sample, we get gradual change over the full, or rather a gradual decline in stability over that full 20-year period, and no real clear plateau. There seems to perhaps be an asymptote that's occurring at 19 to 20 years, but of course we would need even more follow-up to confirm that. And really what we're seeing is just this gradual decline in stability over time. And then when we look at the PTSD cases, as one might expect, with those with higher symptom severity at intake, we see even less stability in symptoms over time. So more true change as time progresses. So this general trend, of course, is not consistent with that set point theory of PTSD symptoms. Here's the same longitudinal stability plot, but for the full sample, for those who weren't interviewed, for the PTSD cases and the controls. Again, nothing particularly striking here. No one case, or rather, no one clinical group stuck out as being consistent with the set point theory, even the PTSD controls. And then Evelyn's groups, which I'll refer to for shorthand. This subthreshold cases look a lot like the PTSD controls, which were more stable but still gradually declined compared to the remitted cases in the current PTSD cases. All right, which we see a decent decrease there compared to the controls and the subthreshold cases in terms of the rate of decline and longitudinal stability. So now moving on to average direction, rate and shape of change. So to address this research question, estimated a series of linear mixed effects or multi-level models. You can see the equations there on the right, with increasing complexity in each model, adding different fixed and random effects, and then linear change, and then different forms of nonlinear change, including quadratic and cubic polynomial terms. Then after that, took the same series of models, but estimated latent class and growth mixture models that allow for different classes or groups of change, and allowing those trajectories and parameters that you're seeing in those equations to change across those groups. And then finally, estimated a generalized mixed effects model with a log link and a gamma distribution. So this was done to better account for the non-normal distribution of the PCL scores. It's less censored, it's positively skewed, and all of the above models, linear mixed effects, latent class, and growth mixture models assume normally distributed errors. So we wanted to see if we got significant improvement in fit with that generalized mixed effects modeling approach. All of these models were compared using information criteria, AIC, BIC, sample size adjusted BIC, and then, of course, plot average trajectories across our groups. And I should probably mention at this point that what is really canonical in PTSD literature is what's sometimes referred to as the cat's cradle. So this is people finding a 4-class solution, either with latent class mixed models or growth mixture models. And what the cat's cradle refers to is, of course, that little game with strings that we used to play when we were kids. And what you end up forming when you play cat's cradle is something that looks like a top line, string goes across the top, string goes across the bottom, and then a crisscross in the middle. Okay, so you get a stable high group, you get a stable low group, you get an increasing group, and you get a decreasing group. That's sometimes colloquially referred to as the cat's cradle. So of course, this is forcing subjects into these mutually exclusive trajectory groups. It has, I guess, the benefit of you get 4 different lines through your longitudinal plot instead of 1 line, but it is forcing people into these mutually exclusive groups. And once they're into those groups, of course, it doesn't tell you anything about the individual. It just tells you about their group membership. And there's been a handful of simulation studies that have demonstrated that these models are highly sensitive to the shape of the distribution of the dependent variable. There's even slight deviations from normality. It can lead to the over-extraction of latent classes. And this is why I particularly had interest in comparing the generalized multi-level or mixed effects model to the growth mixture and latent class models, with the thought that if we're better able to approximate the distribution of the PCL scores, we might find evidence in favor of a continuous single class model instead of these multiple latent class models, right? The quote, cat's cradle that everyone sees. So here's the fit statistics with a focus on BIC, comparing the generalized mixed effects models that I just described to the parametric latent class growth analysis and growth mixture models. G refers to the number of groups, abbreviations, MLM for multi-level model, latent class growth analysis, LCGA, GMM for growth mixture model. I've highlighted in bold the 2 lowest information criteria there. And what you can see is it's the generalized mixed effects model that ends up winning the day. So this isn't really groundbreaking, but I hope it's kind of ice-breaking, and that maybe if people start to implement generalized multi-level models a bit more often than just sticking with their linear counterparts, you might end up finding that you don't have such strong evidence for these latent class solutions that have become so popular in the literature. And if for those who are wondering and have perhaps seen these latent classes emerge in their own data, if we do plot the 4-class solution from the growth mixture model, there's no cat's cradle anyways, right? Okay, so this is what the solution from the 4-class growth mixture model looks like. You can see clearly there's no cat's cradle, right? So really we're just seeing like continuous variation then plotted into 4 different classes. But I mean, we're seeing essentially identical trajectories, the slight decline in the lowest group, but roughly similar trajectories, just major differences in intercepts. So even if you, for theoretical reasons, wanted to, or practical clinical reasons, wanted to prefer and select one of those latent class models, with our 20-year largest and longest study of PTSD, you don't get the cat's cradle. So what do you get? Well, what we have here is plotted for in the full sample blue and in PTSD cases in the red. The observed means, okay, so these are the X's with their 95% confidence intervals, the vertical bars, and then the dashed lines, that's the line of best fit from that generalized multi-level model. And the shaded regions are the 95% confidence bands. So this is both informative in terms of, you know, what does the average predicted trajectory look like? And this is also in some sense a plot of model fit, right? So we see the dashed lines there capturing the average trajectory for cases and in the full sample. And you also see that it's doing a nice job at capturing the observed means at each year, progressing from 1 year all the way to 20 years after 9/11. The other thing you might notice is that, hey, this looks a lot like the sort of trajectories we saw for the prevalence of clinically elevated symptoms, right? We saw that inverted U or arch-shaped trajectory. It's relatively flat, but still there in the full sample. But when you look at the PTSD cases, it becomes visually evident. Here's the same predicted trajectories juxtaposed with the observed means. For the full sample, those who weren't interviewed, the PTSD cases and the controls. The controls are the lowest, quite flat. Those who weren't interviewed look like the full sample. And there are the PTSD cases, quite elevated and with that pronounced arch-shaped trajectory. Again, peaking in roughly 10, 11 years after 9/11. And then finally, here are the predicted trends from that generalized mixed effects model using Evelyn's groups for stratification. So current PTSD, the controls, the remitted cases, and the subthreshold cases. And I've, again, put here the predicted trajectory plots from that psych medicine paper. And you can see that the 20-year trajectory analysis is in many ways replicating this analysis here, even though it was done with the linear mixed effects models. So, right, these trajectories end at 13 years. And then if you can shift your visual attention from that small graph on the left over to the big one on the right, you can see that for most cases, or at least most of these trends, the trends are kind of continuing onward as one would expect if they were to just hand trace out the lines in their sort of continued predicted trajectory. With the one exception being the remitted cases. There's in Evelyn's paper, there was a little bit more of an arch shape, and the generalized mixed effects model has that kind of stabilize out closer to 9/11 and then gradually decline. But it's nice to see this, right? That we're not getting anything that's crazy. It kind of passes the smell test for what we might expect to see in terms of average direction rate and shape of change over this 20-year period. So the next thing I wanted to run was a sensitivity analysis, right? Because we have open enrollment with the World Trade Center responders. So individual subjects don't have the same year of intake. Some responders joined the first year after 9/11, and then open enrollment continued, and you get more and more and more, baseline visits at every single year. So the question was, well, are these average trajectories in the full sample, do we see that substantially impacted by the year of intake that responders enrolled and provided their first PCL? 2002, we really didn't have enough folks, too few to add that line, but starting at 2003 on to 2021, right, we can see that there's not much of an effect here in terms of intake on the predicted trajectories. They kind of all blend together. The shaded regions in gray are the 95% confidence intervals. You can see that there's no one given stratified predicted trajectory that's significantly different from any of the other. It's just all a whole bunch of overlapping gray regions. So this is encouraging that the year of intake didn't somehow substantially biased our estimates of the average direction rate and shape of change. So what about individual prediction? Okay, so on the left panel here, we have our observed symptom trajectories for a subsample, random subsample of our World Trade Center responders. Each line is a different responder. These are sometimes called individual trajectory plots or spaghetti plots if you're like to have a little bit more fun. Each dot within a line is an actual observed PCL score, right? So on the left, we have the observed spaghetti plots, and then on the right, we have the predicted spaghetti plots. So you can see how the observed data is quite noisy. The PCL is a noisy instrument. This is to be expected. And you can see here that the best fitting quadratic generalized growth model smooths over much of that noise. So you get smooth arch-shaped or smooth U-shaped trajectories, given that quadratic fixed and random coefficient are allowing for a bend in our trend line. So here's another way of looking at individual prediction. So now we have observed scores from 20 randomly selected responders with predicted trends from the quadratic multi-level model. That's the red dashed line, and that's the linear or parametric model. And then also the black line, which is that generalized quadratic multi-level model with the gamma distribution and log link. The blue dots are the observed PCL scores. Okay, and x-axis is time, number of years since 9/11, y-axis is the PCL scores. So you can see that for responders who had relatively stable symptoms over time, the model does an excellent job at recovering their predicted trajectories. Again, this is not only shedding light on what does individual variation around the average trend look like in terms of individual prediction, but also how well does the model fit the data. So you can see it does it for most of these cases. It's doing quite a good job at capturing variability. A couple of folks stand out. This one top far right, where someone's kind of crazy all over the place, bouncing up and down in terms of their self-reported symptoms. Another one, 1, 2, 3, 4 to the right, 3 down. We get another responder who's bouncing up and down in terms of their symptoms. For those folks, we of course have much larger residuals, much larger errors in terms of prediction. But on the whole, overall good fit to the observed data. The other thing that we can observe here is that what's happening in the generalized model with that log link is it's pulling the predicted trajectory away from extreme scores. So if we look at second column, third row down, we can see an individual responder who starts off with a couple of really high symptoms, and then symptoms start to decline in later years. And then this is really when we see the predicted trajectories from the parametric model and the generalized model diverge. And you can see that the parametric model is getting pulled up closer to those extreme observations, where the generalized multi-level model with that log link isn't getting pulled to those extreme scores in such a pronounced fashion. So here's what the individual prediction looks like for PTSD cases. Again, for those folks who are diagnosed with PTSD and have a relatively stable self-reported trajectory, the model does a really great job at recapturing it. And then for those who are really sporadic in their self-reported symptoms, you see more error. And then here it is for controls, and where it's really doing a great job with controls. We see very little residuals from the line of best fit when we're looking at the individual prediction for the PTSD controls. So just some kind of summary notes on the models and the predicted trajectories, the generalized mixed effects model. So we can predict PCL scores at any time point for every responder with a baseline PCL, but of course there is error in prediction. Our sample size grows considerably from 2002 to 2020, and prediction is better from 2010 to 2022 when the sample is larger than it is from 2002 to 2009. This is no surprise. We have larger margins of error for responders with limited follow-up and high within subject variability. And as I mentioned before, that log link is pulling in those extreme scores to decrease their impact on the estimation of the line of best fit. The predicted scores will more often underestimate symptom severity than overestimate because of that log link. And this is particularly evident for predicted baseline scores. And responders with really high baseline PCLs in recent years, the quadratic function is pulling their baseline scores downward to really make them look like long-term increasers, even if they start off high in 2010 and then decrease from there. If you're looking at the full predicted trajectory, the quadratic function is going to extrapolate backwards like this. So then overall, they look like a long-term increaser, even though perhaps in 2010 they were quite high and now they're starting to gradually decline. So these are some of the sort of caveats or limitations of our model. And how can it impact clinical translation if we're thinking about using these predicted trajectories to, for example, identify those who are at risk and who have poor long-term course and perhaps to require some additional attention and follow-up. So here are some examples, just like I said, of poor long-term course, not in terms of prediction, but just in terms of how responders are faring. So increasing trajectories, So here it's the same plot, but the line of best fit stops within the observed data range, and it really provides a visualization of what I was just describing. All right, so if you look at number 64 here, top row, third column, right, you can see that, I guess in this case, they started low, popped up high, they're coming back down. But if you look at the extrapolation at 1, 5, and 10 years after 9/11, the quadratic term is pulling that down. So they look like a long-term increaser. Again, these are folks who, based on percentiles of long-term predicted course, are considered bad cases, bad long-term prognosis. Considerable variability, of course, in how bad each of these are. And if we focus on these top three, I think these three are kind of emblematic of what we're going on, or what we have going on for predicted long-term course. We have some ambiguous or sort of questionable cases, so that they're high at intake and they're rapidly declining in terms of their observed scores. But the predicted 20-year course, the quadratic trend and 20-year increase, again, they look like they're a long-term increaser. And most of the scores are above that clinically significant or relevant threshold at 44 on the PCL, but their most recent score is below that threshold. Then we also have these sort of sub-threshold cases where they're really low at intake and there's this gradual increase over the 20 years. So they're getting worse. They started off not too bad, but they're gradually getting worse and worse in terms of their symptom severity over time. This is a positive trend and a 20-year increase. And then finally, when we look at percentiles of predicted change over these 20 years based on our generalized model, we also get a handful of really clear cases, right? So in this case, this responder was high at intake, and they have a positive trend and a 20-year increase. All predicted trends and all observed scores exceed the threshold. And compared to the initial intake, the symptom trajectory is increasing over time. So now that we've looked at, these average trajectories and some individual trajectories and some model fit, what do really atypical trajectories look like? Okay, so what did I do to try to visualize or get a handle on atypical trajectories? Well, one is you can just plot random samples of responders and their predicted trajectories, look at the full sample, look at cases, look at controls. Another option would be to plot trajectories at the boundaries of our growth parameters. So we have a random intercept, we have a random linear term that captures linear rates of change over time. We have a random quadratic term, captures individual deviations from the average quadratic rate of change over time. So we can say, well, what do the trajectories look like in the top 1% and the lowest 1% of the random intercept? Top 1% and lowest 1% of the linear slope, top 1% and lowest 1% of the quadratic slope. And then finally, we can plot trajectories at the combinatorial extremes of these growth model parameters. Right, so you can take them, square them, add them up, take an average, or you can take them and take their absolute value and add them up, take an average, and then you're getting, and then after you have that composite of the combinatorial extremes, plot the folks in the upper and lower 1% to see what the most atypical sort of 1% of responders look like. So here's the individual trajectory plots for a random sample of cases, random sample of controls, no major surprises there. Right in the random sample, we get a sort of smattering of high and low. With the random sample of cases, trajectories are more elevated. We see that more pronounced arch-shaped trend. And then the random sample of controls, that relatively stable, relatively low, with a whole bunch clustering right at the bottom of the PCL, with really no predicted symptom severity over the 20-year course. Well, here's what atypical trajectories look like in the full sample. So these left two panels, these are folks who are in the lowest 1 percentile of their baseline. So intercepts. Then the lower and upper 1% for the linear slope, and then lower 1% for the quadratic slopes. So what do we see here? We see rapid decliners for that 1% and the linear slope. Obviously, the 1% for the linear slope, we see these rapid incliners who then have that quadratic term begin to stabilize them a little, if not revert their trend a little bit. The linear slope and the quadratic slope are negatively correlated. So this is what we would expect. And then for those in the most extremes of the random quadratic term, we see really pronounced either U-shaped or ARP-shaped trajectories. So the big benders in the sample. Here's the same plots except for PTSD cases. And in this case, it's the upper and lower 5% because we had fewer cases to plot. Same general trends are evident for PTSD cases. In terms of what's to be expected for atypical trajectories over 20 years. And then finally, here's a plot of the predicted trajectories at the combinatorial extremes of the growth model parameters. Here we have PTSD stratified in terms of, or colored rather, in terms of the PTSD controls, the cases, and those who weren't interviewed, right, had missing data for their clinical interview. And again, and what we're mostly seeing here is what we saw at the extremes of the quadratic term for atypical trajectories, right? We see really steep increases in arch-shaped trajectories, and then we see these atypical U-shaped trajectories, people who started high, got better, and are now getting worse again. Another way of thinking about and trying to visualize atypical trajectories when you don't have multiple latent classes, that is one of the benefits of the multiple latent classes, right? Is you get a certain percentage of the sample that's in each of the classes, and you say, hey, this class only has 7% of responders. Look, this is what that class looks like. These are the atypical cases. Right? You don't have that nice visualization when you stick with a continuous model that only has one class. So this was a plot that I came up with to try to, again, visualize what the distributions of change look like over different time lags, and also stratified or grouped by what their PCL score was at intake. Okay, so the x-axis now is predicted change in the PCL total score. The y-axis is the time lag. So 1 year, 5, 10, 15, and 20 years. And then each of these different graphs is a different PCL grouping for folks who were 17 to 26, quite low at intake, 27 to 36, and so on. And what we can see is that the distributions of predicted change over this 20-year time period trend towards improvement, which is encouraging, right? Especially, of course, as you move up higher, those who start really high, there's not too much room. There's not only so much room to get worse, right? And again, because intercepts and slopes are all correlated, it's another reason for wanting to stratify these distributions of predicted change across these different levels at intake. But you can also see that for a subset of folks, I've highlighted the tails of the density plots there in red. There's a subset of folks for whom long-term predicted course is quite poor. Although the general trend in the cohort is towards symptom improvement over the course of the 20 years as time moves further and further away from the trauma, we do have a subset of individuals who just aren't getting better. And if you're wondering and you're thinking, oh, well, this could be a little bit dubious or misleading, these are predicted scores. Some folks prefer the predicted scores over the observed ones because they think it's smoothing over a lot of that noisy error that's in the observed scores. Some people don't trust the predicted trajectories. They just trust the observed scores. Okay, so here's what the distributions of long-term change look like with the observed scores. And we can kind of flip-flop back and forth. Now, in this case, because they're observed scores, I had to bin the y-axis in terms of 1 to 5 years, 5 to 10 years, 10 to 15, and 15 to 20, instead of just precise predictions at 1, 5, 10, 15, and 20. But the same general pattern of results is evident, right? Where there's, as time progresses, the distributions of change are shifting towards improvement, but you have like 10% roughly or so, little above, little less, depending on where people start off at baseline. But you get a subsample of folks who have poor long-term course in our cohort, which of course is discouraging and concerning. So next, moving on, how quickly do our symptoms get better? Okay, so here we have a Kaplan-Meier survival plot, obviously inverted. Number at risk at the bottom, years since intake on the x-axis, and the probability of symptoms improving, which we operationalized as the PCL total score decreasing by 10 points or more. Okay, and these vertical dashed lines that are going up to these Kaplan-Meier curves with their confidence intervals, they're indicating the median time until symptoms have decreased by 10 points or more. Okay, so we can see in the full sample, it's taking about roughly 7 years, okay, in terms of median time until symptoms improve. So that's a long time, right? We need to be patient with responders and expecting to see clinically relevant improvement in symptoms. For PTSD cases, we need to wait even longer. We're talking about roughly 9 years in terms of the median time until we see symptoms getting better. And what about those who weren't interviewed? They're actually doing a little better than the controls. This is now the same plot, but it's contrasted in terms of those who weren't interviewed, the controls and the cases. We might think, oh, maybe folks aren't getting interviewed because their symptoms are so terrible. They don't want to have to go through a skid because it's traumatizing for them to have to relive those experiences and recall them. This suggests no, that isn't what's going on. The folks who aren't doing the skid, it's because they think I'm fine. And in fact, based on their self-reported PCL scores, they are improving in terms of their symptoms at a faster rate on average than the controls and the PTSD cases. Now, how quickly do symptoms get worse? Again, we need to see over 8, almost 9 years of time progress from the exposure until we see a clinically significant worsening of symptoms too. So that's for PTSD cases. For the full sample, you have to get beyond the observed window before we hit that 50% probability of symptoms getting worse. So change is slow. True change takes quite a long time to occur. And again, those who aren't interviewed look like the controls in terms of how long is it going to take until we see symptoms getting worse. So then finally, with the limited time I have left, does exposure severity and genetic liability predict symptom trajectories? Well, here's the results of a linear mixed effects model with level 2 predictors of linear and quadratic slopes. And we can see very small p-values, right? So 0.002, 0.003, and less than 0.001 for the polygenic risk score effect on the linear and quadratic rate of change in symptoms over time, and also for the exposure effect on the linear and quadratic rate of change over time. This holds up in the generalized mixed effects model, right? So whether you want to test those level 2 predictors of random intercepts and slopes, it remains statistically significant, whether it's a parametric mixed effects model or a generalized mixed effects model. So that's encouraging. What does the symptom trajectory look like stratified across levels of genetic liability? Well, the lowest trend line here in blue, that's 2 standard deviations below the average for the polygenic risk score for PCL total scores, then moving upward to -1, mean, +1, and +2 standard deviations. So we see, again, this sort of fanning out of the predicted trajectories across levels of polygenic liability. And here's what that fanning out looks like for exposure severity. So in this count for exposure severity, we used a count of 8 traumatic exposures. These were things like arriving at the site early, being near the towers when they collapsed, handling human remains, being exposed to blood or bodily fluids, knowing someone who died, being physically injured at the site, sleeping on the pile of debris and rubble at ground zero. Okay, so these are all just a count of their psychologically traumatic exposures. Although exposure severity did have significant impacts on the random intercepts and slopes, you can see that the effect is larger for exposure severity on the intercepts. So you see more of the fanning occurring right at the y-axis, right, when symptoms were first measured. So exposure severity has a more pronounced effect on where folks are starting off. And then also, you can see has some impact on the rate of change over time. And it's the polygenic liability that is in a slightly stronger fashion driving what the symptom trajectories look like after that initial fanning of the symptom severity occurs at intake. So here are the same plots now stratified across the PCL subscales. So we can break out the PCL total scores in terms of hyperarousal symptoms, re-experiencing symptoms, avoidance symptoms. The hyperarousal symptoms basically just look like the PCL total score. But when you tease out the re-experiencing symptoms and the avoidance symptoms, this is where we start to see differences in trends. We see the same fanning and in the expected directions in terms of higher genetic liability, worse trajectories, higher exposure severity, worse trajectories. But the re-experiencing symptoms are gradually declining over time, perhaps because the responders are learning coping techniques, or rather are avoiding re-triggering thoughts and experiences that would flare up those re-experiencing symptoms. And that we see with the increase, more pronounced increase in the avoidance symptoms over time. So then finally, to the last question of the presentation, does PTSD predict mortality? Well, here we have the results of a Cox proportional hazards model where we've controlled for age, we've controlled for gender, and then here we have the PTSD clinical status. So you're not diagnosed or you're a case, and yes, PTSD case status does statistically predict an increase in the hazard rate of mortality in our responders. If we break out the case status into Evelyn's groups, it's the current cases as opposed to the remitted or threshold cases where we see a significant increase in the hazard rate of mortality. And then finally, if you look at the linear rate of increase in symptoms over time from our predicted trajectories, the more rapidly you're increasing in symptoms over this 20 years, the faster or the higher the hazard rate of mortality. So what were our responders dying of? For those who had an increased rate in the mortality, as expected, there's sort of wide array of different causes of death. Ones that stick out: suicide. 6 died to suicide, 13 died to heart attack. We have 22 cases of cancer and a handful of folks where it wasn't recorded. And other than that, you get a kind of smattering of random causes of death. So, summary of these very extensive analyses: we have a yearly prevalence of clinically elevated symptoms from 2002 to 2022, roughly 8 to 15% over those 2 decades. How stable are symptoms? Well, they're less stable than height, weight, and BMI, but they're about as stable as blood pressure and personality traits, but not so stable as one might expect for a set point theory. In terms of average direction, shape, and rate of change, we have a slight increase followed by a decrease, ending at roughly approximately initial levels for the full sample. And do we need multiple groups? No, we don't. There's no cat's cradle. Individual trajectories characterized, rather the atypical ones are characterized by rapid and extreme incline or decline. How quickly do symptoms improve or worsen? Very slowly, typically 7 to 9 years. And does exposure severity and genetic liability predict symptom trajectories? Yes. Does PTSD predict mortality? Yes, both PTSD diagnosis and the rate of change of symptoms over time. And that's all I have for you for the limited time we have left. I'm happy to take any questions.
Wonderful. Thank you, Dr. Mann, for that informative presentation.